We already know about inverse functions when we learned basic arithmetic. The inverse of addition is subtraction. The inverse of multiplication is division. The inverse of an exponent, say like 2 squared, the inverse of this would be the square root. So exponent goes to square root. What all of these things do is they undo the other operation. They're very important for our mathematical structure. We kind of always have to have this idea of inverse. And functions are also invertible as long as they satisfy certain properties. If we take an addition function, say f of x equals x plus 2, then its inverse, it satisfies a certain property, its inverse would be x minus 2. We can tell they are inverses by doing this. F of g of x, I'm plugging g of x into f of x. We have x plus 2, so x is going to be x minus 2 plus 2, x minus 2 plus 2. We get x, and g of f of x equals, plug in f of x into g of x, and we get x plus 2 minus 2 gives us x plus, oops, I meant the parentheses to drop, x plus 2 minus 2, and those cancel, of course, giving us just x. As long as both of them give us x, they are in fact inverses of each other. This is the definition of an inverse. They both have to be true, not just one. One of them can be true, but if the other one is not true, then it is not an inverse. So let's consider, let's see, k of x equal to 4x plus 9, and L of x equal to x minus 9 over 4. Are they inverses? Well, we just take k of L of x, meaning plug L of x into k. We get 4 times L of x plus 9. Get a little more room here. These 4's cancel, and we get x minus 9 plus 9, which of course cancel to give us just x. So that's a good starting point, but it does not mean that it's inverses yet. L of k of x. L of x is, sorry, we're plugging in k of x into L of x, so we have 4x plus 9 minus 9 over 4. You see the parentheses don't matter here, so we can drop them, and we get the minus 9 plus 9 canceling. 4x over 4, which of course those cancel, and give us just x. So we've proved they are inverses. Okay. Let's look at m of x. Let's do a different variable. Let's do a. M of a equals 3a minus 7, and n of a equals a plus 3 over 7. Okay, are they inverses? All we have to do is plug them into each other and see what we get. Plugging n of a into m of a, we get 3 times a plus 7, or a plus 3 over 7 minus 7. Distribute 3 in there, we get 3a plus 9 over 7 minus, I'm going to change the 7 into, I'm having a common denominator. So it's 49 over 7. 3a plus 9 minus 49 over 7. This gives us 3a minus 40 over 7. And that cannot simplify any further. What we want is a, but this thing does not equal a. And so we can stop there. We don't even have to check n of m of a because they're not inverses. Sometimes one way does work. It's odd when it does, but sometimes it does, and sometimes the other way doesn't. But if once you find one of them doesn't work, then you can immediately stop. Not every function has an inverse. Only functions that are 1-to-1, that's the special property I was mentioning earlier. 1-to-1 also means or that no two values of x are equal the same thing. So for instance, we have two functions here. We have f of x equals 2x plus 1 and g of x equals x squared minus 2. This function here, f of x, this is 1-to-1, whereas g of x is not 1-to-1. That's because I can draw what's called a horizontal line test. I can do the horizontal line test by drawing a horizontal line. You can see here, this line only crosses once, and I can draw any horizontal line. In fact, you have to make sure you can draw any horizontal line everywhere over the function, and it'll only cross once. This one will only ever cross once. But you can see here, it crosses twice. And that means this is not a 1-to-1 function. Because of this thing has no specific inverse. It does have an inverse, but we have to do restrictions on it. We have to actually restrict the domain to be only from 0 to positive infinity. If I were to show you that, say x greater than 0, make sure my what I'm writing is correct. So I can restrict the domain to being x greater than or equal to 0. And you see now this is a 1-to-1 function. But I've had to restrict the domain, and it's not the entirety of it, so it's kind of like less information. But the original function is not 1-to-1, therefore it does not have an inverse. The horizontal line test is very similar to the vertical line test, which says if something's a function. This, of course, is a function because any vertical line crosses only once on g of x here. But you can test, there's only one horizontal line that does not cross once, which is y equal to -2. This only crosses it once, but every other horizontal line does, and so it's not 1-to-1. If a function is 1-to-1, then we can find the inverse by replacing the function notation like f of x or g of x or g of y or m of a or whatever you might have with y. I'm going to replace f of x with y and then flip x and y. So this only works if a function is 1-to-1. How do you know if it's 1-to-1? Well, either it's going to be given to you, like I'm telling you that this one is 1-to-1, or you just graph it and use the horizontal line test. So once you have flipped x and y, now we just solve for y. So we have x plus 1 equals 3y, divided by 3, and we get, let's do it over here, y equals x plus 1 over 3. So I can rename y, instead of just leaving it as y here, as f inverse of x. That's the typical notation we use there. These two things are inverses of each other. I've shown that algebraically here, but I can prove it, if you're not convinced, by just plugging each into each other. So plugging in f of -1 into the other one, we get 3 times x plus 1 over 3 minus 1. 3's cancel, and that gives me x. Plugging it the other way, I'm going to be plugging f of x into -1 here, into f inverse of x. Parentheses drop and the 1's cancel, giving me 3x over 3. And of course those cancel to give me x. So that proves their inverses right there. That's how we do it algebraically. Let's do another one. So let's say m of, I don't know, let's do y now. M of y equals x plus 2, not x, it's y cubed. I guess y is a little bit confusing. Let's just leave it with x. That's probably the thing you're going to be using the most. And say this is y. Now to solve for the inverse here, I'm telling you that this function is 1-to-1, so we can immediately solve for the inverse. We get y equals x plus 2 cubed, and flip them. Now we solve for y. The first thing I'm going to do is take the cube root, because that cancels with the cube. Now I can subtract 2. And we get y equal to the cube root of x minus 2. And so I can kind of remove this y here, remove this, and I say m inverse of x. These are inverses of each other. If you want to prove it, just plug each one into each other and you'll see that you get x as the final result. Now, a more interesting problem is when we have a rational function. Let's see, x plus 1. Okay, I'm going to change this to y again, and then flip the variables. So if we have y equals this, that means each one of these x's are going to be flipped to y. We have 2y minus 3 over y plus 1. Now we want to solve for y, but we have 2 y's, meaning we need to get the y's to one side. The first step I'm going to do here is multiply both sides by the denominator, x plus 1. That cancels, and now we have just a function that's doesn't have any division in it. Distribute the x. That gives me, I'll do xy plus x equals 2y minus 3. And now we can get the y's by themselves on one side of the equation. Let me get some more room here. Xy plus x equals 2y minus 3. I'm going to subtract the 2y to this side and subtract the x to the other side. That gives me xy minus 2y equals negative 3 minus x. And now you see here, I can factor out a y. This is very important because now we only have a single y, and that means we can solve for it. The way we solve for it is divide by x minus 2. Y equals negative 3x minus x over x minus 2. And I can rename this to g negative 1 of x, or g inverse of x. So these two things are inverses of each other. This one takes a little bit more work to prove it if you want to, convince yourself. Now I'm going to take these functions and graph them and show you geometrically how we see that they are inverses. Okay, here I have our functions graphed with our inverses. And you'll see this is the first function we had. This is f of x equals 3x minus 1. Now I can't write this as f inverse of x. That's the proper notation for it because Desmos's doesn't recognize the inverse there. So I'm just going to delete that. And it's going to be named both f of x, but it doesn't really matter. It's just for, sake of understanding that these two things are inverses of each other, not the other ones. And you see that the blue is the inverse of the red, and vice versa, actually. The red is the inverse of the blue. And you may not see the geometric way of seeing this, but if I draw this bottom function here, y equals x, which is just a linear function of x, you see that red and blue are flipped. It's a mirror image over this, this y equals x line. If I flip it over that, I get the exact same thing. Let's look at the next two. M of x equals x plus 2 cubed, and then the cube root of x minus 2. you see that these are also inverses of each other. They look exactly flipped. It's this cool arrow thing there. Huh. And yeah, so they're inverses. And the final two, this one's a little bit harder to see, but if you were to flip this red line here across this axis, you would flip it and it would go right down here. So this red line goes to this thing, this blue line, and this red line flips to this blue line here. These are inverses, it's just a little bit harder to see. What you'll also notice is that here we have this special point, this is the y-intercept, which is 0, 1.5. If you flip over to this red line, it becomes an x-intercept of the inverse, which is 1.50. The same thing with this x-intercept of -3, becomes a y-intercept of 0, -3. All we really do here is flip the x and y values. That's the reason why it's across this line here. This line is when x equals y. And so all of those things will never flip. They're just going to stay the exact same. But all we're doing here is just taking every one of these values here. Yeah, I showed you the special ones. We're just flipping x and y, and that's what gives us these values here. Hope that makes sense. And this is just a little bit of a teaser for next chapter. We're looking at these types of functions here, which are called exponential functions. In this case, I have 10 to the power of x, and that gives me this behavior here. It's got an asymptote, a horizontal one, right at 0, but it does go on up, and it will eventually get to all of these values. So it actually has a domain of everything. And its inverse, we flip it along this line, gives us the logarithm. The inverse of an exponential function is a logarithm. That's not the same thing of the inverse of an exponent is a root. That's because when we have an exponent, we're looking at something like x to the power of 2 and the square root of x. The square root of x. Those are inverses of each other. Well, with some caveats to the fact that x to the power of 2 is not invertible. But these have a number in the power, in the exponent. These ones have the variable in the power. And so that's the difference between exponential functions and these types of exponents. These are called polynomials. These are called exponential functions. But we're going to be studying these types of functions, the exponential and logarithmic, because they have a variety of applications.